Okay, so now in this video, we're going to go over what we can do when we have a function that's not one-to-one and how we can make it one-to-one and why it's important for inverse functions that this be the case. So let's look at this common trig function, the sine function, and let's first start off by showing that it's not one-to-one on its entire domain. So let's draw a sketch of the sine function, which you should be very comfortable with. Remember that it does this cool thing where it goes up and down, and it goes over and over like that, right? Y is equal to the sine of x. Now, the domain for the y equals the sine of x, remember the domain is all real numbers. The domain goes from negative infinity to infinity. The range, though, remember, caps out at +1 and -1. Now, remember what one-to-one means. One-to-one means that you won't have the same y value appear more than once. You won't have the same y value repeat for different x values. So let me draw this. That's the origin to make it clear. So here, and let me highlight the key points that we can refer to. Remember 0, here's, it goes up, then it goes down, it becomes 0 again at pi, and then this is 2 pi. Over here is negative pi. Now over here, pi over 2, comma 1. And over here, negative pi over 2, comma -1. So what's the deal here? Well, the deal or the problem with this is that we can show that the y value of 1 occurs for multiple points. The y value of 1 occurs when x equals pi over 2, but it also occurs over here when x equals -3 pi over 2. And over here when x is 2.5 pi, or for these points down here, when x is negative pi over 2, y is -1, but also when x is 3 pi over 2, y is also -1. So there are multiple y values, there are multiple x values that give the same y value. Like you can show easily that f of negative pi over 2 is equal to f of 3 pi over 2. And keep it going, we can go further. That's all we need. We can have one violation and equal to -1. We can show there's many points here, 0, pi, at 2 pi. F of 0 equals f of pi equals f of 2 pi equal to 0. So again, this is not one-to-one. Not one-to-one. And again, remember the horizontal line test? Maybe think of it that way, the horizontal line test. Anyways, now, so what can we do? What can we do with the sine function to, take care of the situation? Because remember, if it doesn't satisfy this one-to-one condition, that means it can't have an inverse function. So we need to find a way to make it one-to-one. So what we do is we restrict the domain. We restrict the domain so that it is one-to-one, so that the y value never occurs, the same y value never occurs more than once. So if we restrict the domain to negative pi over 2 to pi over 2, so let's draw a sketch over here, right below. If we go only from negative pi over 2 to pi over 2, so we would be down here, and the pi over 2 up there. So we got pi over 2, 1, and we got negative pi over 2, -1. If we restrict the sine function to this domain, then it's going to be 1-to-1. You can see that there are no y values that repeat. There's never going to be a y value of anything here or here that's going to occur more than once. So the y value of pi over 2 occurs only once because it never goes beyond this. It's not we're going to stop the cycle, and we stop the cycle over here, so the y value of negative pi over 2 never occurs more than once. So essentially, we've cut off the domain to be from negative pi over 2 to pi over 2. The range, though, stay the same. Oops, negative. Negative pi over 2. What am I writing? -1, the range stay the same from -1 to +1. And I should be putting brackets around this one as well, because we're including those. There we go. So the domain restricted it to this interval, and the range happened to stay the same. So this is 1-to-1. Now, so why do we care about this? Why is this important? Well, because the reason is if we want to have an inverse function. So when we have this, restricted to this domain, the inverse function will exist. And that means, we can, well, down the road, we're going to go later in this chapter, we're going to find the derivatives of these inverse trig functions. But if you remember, maybe from your pre-cal days, hopefully you remember what the inverse trig functions look like. And if you were like me, when I first saw those things, I was like, what the heck? Why are they so why are they cut off? If you notice, the inverse sine function wasn't like going on forever like this. Instead, it didn't do exactly this, but what it did, let me use green. It did this. It was cut off. It was like, the heck? F inverse of x. And you remember, like, we use that little -1 power of that. And you may see it in your calculator, or also written as the arc sine of x. It means the same thing as the inverse function of the sine of x, the inverse of sine of x. Remember, it's not sine to the -1 power. This is the symbols of how we write the inverse sine function of x. Now, remember that if this is restricted to this domain, the reflection of this geometrically, you can just think about it. If we reflect this line, or we reflect this graph across the line y equals x, this is just to give you a little like visual. Reflect this line over this line, reflect that line over that line. Think about how it's going to look. It's going to be like that. Now, what would this point be? Think for a second. It's going to be 1, pi over 2. Not pi over 2, 1, 1, pi over 2. And this will be -1, negative pi over 2. So then the domain of the inverse function is the range of the original function. So the domain becomes -1-1, and the domain becomes -1-1, and then the range becomes the original domain. So the range becomes -pi over 2 to pi over 2. Now I'm going to remind you of this when we go through the last section in this lesson or in this chapter, because this really made a lot of sense to me once I learned this, because I always saw those inverse trig functions being like little pieces, and like what the heck, why are these little pieces, what's going on? And this is why. So there you go.